Okay, in this video we're going to take a look at the measurements and calculations involved in spheres. And these are actually some of the easiest ones to work with. They're more obsolete. You don't see them as often, so it's a little tougher to remember. In fact, we deal with cylinders and even cones, it seems like, a lot more often than we do spheres for whatever reason. So people forget about the formulas, but actually implementing these things is quite a bit simpler than some of the other ones we've worked with. So let's take a look at volume. Okay, here's a sphere over here. Has a radius of 3. Now remember, we're talking about a three-dimensional object here, so it's like a globe or a basketball. We're going to be looking for the amount of space inside of that. So if I were to take some sort of perfectly round ball type figure and fill it up with water, how much would it take? That's what we're looking at for volume. Okay, so I've got a radius of 3, and I just made that number up. It could represent feet, inches, miles, who knows, whatever. But I didn't put any units with it because I just wanted to do a generic example for you. Okay, now if I were to take this problem and I plug in 3 right here for the radius, and notice there's a lot of 3's here all of a sudden. I did that on purpose. I want you to see how to basically go through the correct order of operations and not get confused by all the numbers that look the same. Okay, so let's write out what we have. 4/3 pi. Now remember, that is right here. The exponent applies only to the radius, not to the pi and not to the 4/3. So I have 3 cubed. Okay, now 3 cubed is not 9, but that's what a lot of people will accidentally put, especially when they get moving fast. Okay, I'm going to erase something here to make sure we don't accidentally confuse it with something else. Okay, now let's look at what would happen. This piece right here, 3 cubed is 3 times 3 times 3. That's 27. So I really have 4/3 pi times 27. Okay? And if I were to rearrange this a little bit, put it in a different order, I could have 4/3 times 27 over 1 times pi. Okay? And I could multiply 4 times 27 and divide by 3 just like I would on a calculator, but I noticed it might be a little easier to do this. Notice that there's a common factor. I could divide them all by 3, and this becomes a 1, and this becomes a 9, and now my numbers are a little easier. I have 4 times 9, which is 36 pi, and we're talking about volume again, so this is units cubed. I put a U there, but that would be inches, feet, whatever it might have been in your particular problem. Okay. Now surface area, don't assume this is any worse. It's a little tougher to remember because you just don't see it that often, but the radius is 3. Okay, I got that right there. So I can put the radius right here. Here's my formula. It's basically the same kind of thing. I don't have a fraction, and I got one less exponent. So this is 4 pi times 3 squared. And I would say the only thing you really got to watch out for is that you only square the 3 and then multiply it in. Don't multiply everything together first and then square the whole result. That makes a completely different scenario. So this would become 4 times pi times 9, which once again gives us 36 pi, and in this case it's units squared. Now, the reason I picked this example is it's very common in a geometry class to see things like this and assume there's a big reason for it, that, oh, maybe they're always supposed to be the same, and nothing could be further from the truth. The reason these two things ended up exactly the same is purely coincidental, just because of the numbers or the measurements that were involved. Okay, they mean totally different things. This value right here, okay, if I was talking about, say, a globe, this would say how much paper would it take to wrap around the outside edge of this globe. This right here is saying how much three-dimensional space of water would I have to put on the inside to fill it up. And even though they end up being the same number, that doesn't really mean they always should. In fact, they rarely do. Okay, so I want you to realize that it really is primarily because I picked this 3, and there just happens to be numbers that work well with that 3 in these formulas. That's the reason these values turned out to be the same. It has nothing to do with the way the formula is, and it should always be the same. Okay, so just go with wherever the numbers take you. Here's your formulas. If you can take care of that one and that one, there isn't a whole lot with spheres you can't accomplish.